I'm gonna do. All right. So our next speaker is Zack Jackowski. Zack is the chief engineer on the SWAT team at Boston Dynamics. And he's the GM and the chief engineer for SWAT Dynamics. He's spent the last 5 years focused on transitioning the company's research into quadrupedal locomotion into a successful product offering at a line of business. Over his 11-year tenure at Boston Dynamics, he's led the design of 6 quadruped robots and has been behind the camera directing many of the company's YouTube videos. So we're really excited to have Zack here today.
I am thrilled about your talk because that is almost exactly what I would have said about developing robots at Boston Dynamics, and that's not what I'm going to talk about today, because I figured everyone else was going to talk about how hard developing robust robotics was, and I wanted to talk about kind of the opposite thing, which is what academia looks like from my perspective in industry, and how we derive value from academics, and what the world could look like if those of you who are PhD candidates right now decide to go into academia instead of industry. So let's go right on. In fact, your thing about that mile-long trajectory was like exactly the kind of thing we do all the time, and I was like betting, was it what you said about discretization, or was it a numerical issue about not anticipating that length of trajectory? You might be here because you want to go into industry. That's awesome. I love industry. I abandoned my professor after finishing my master's degree because I wanted to go into industry. But it's not the only way to have a major impact. At Boston Dynamics, we love the professors that move the industry forward. They do super important work, and I think we work together really well. The last thing was, we've been listening to how hard it is to make robots that work in the real world. You can take those problems on from your position in grad school or in academia. But we're really good at that stuff. We have big teams, we do lots of testing, we have people who specialize in software engineering. We know how to work that stuff. There are lots of problems we don't work very well, that we can work really well hand in hand with academia. Just one Easter egg in here. If you ever see someone from Boston Dynamics talk about spilling the beans, it's because they beat this thing into us when we do presentations when we start, from our founder, Mark Rabert. He's got this paper from like 1985 when he was a prof at CMU about how to do talks. And so this was the hook. Hopefully you pay attention for the rest. Our agenda today, I'm going to talk about getting your work noticed. I think that's a place where I actually have some expertise, so we'll talk about that a little bit. That breaks down into having something to show that resonates with your viewers, letting the results speak for themselves and do it clearly, and engage the world directly. Again, your videos rock. I think you were right on with making that good demo video. That's how you really give a company a kickstart. There's a lot of really specific techniques I think folks can use to target impact with industry from academia. We'll talk about how to do that kind of communication. I'm going to talk about some of my pet things that I see happening in academia that I'm really excited about and I'd love to see amped up. And then the last thing at the bottom there, which is if there's time, I'll talk a little bit about testing at Boston Dynamics. Sweet. So who am I? I'm Zack Jackowski. I've been at Boston Dynamics for 11 years. I used to be chief engineer for Spot, means kind of running hardware and software teams as an integrated exercise to bring the product to market. Now I'm general manager, which means I largely drive spreadsheets and customer engagements. And I'm usually behind the camera, CAD, a terminal, or a spreadsheet. And so you never see me in any of our videos. It's rare that I'm getting out into the daylight right now. I did my master's degree with Russ Tedrake at MIT on legged locomotion. And I've got about 400 million YouTube views from sitting behind that camera. So at Boston Dynamics, here's the sales pitch part. Yeah, our mission is to create amazing robots that enrich people's lives. We have multiple product lines. We're a serial robotics product company. Yeah, that's a little bit weird in the robotics space. We're a little bit weird because I think we unabashedly love robots. And we're getting really good at turning that into a series of businesses. So, with Spot, we've got our quadruped robots out in the world, keeping people safe and giving people better insights into their operations in industrial and manufacturing facilities. We have our warehouse robotics product line, which is really robots focusing on making people more productive and pulling them out of genuinely dreadful jobs. Unloading hot containers, getting injured. There's things that robots should obviously be doing that we shouldn't be subjecting people to. And then robots that inspire. We just fundamentally love engaging with the public and making things that kind of connect with people in a visceral way. Like I was saying, Spot, which is the product group that I head up, is really designed for sensing and manipulation tasks. There's no arm on the robot here, but I'll show you a couple arm things. And these robots are getting put to use in factories, utilities installations like power plants and switching yards, chemical plants, and hazmat incidents. And the reason for that is because there's a lot of situations in which a person unfortunately has to suit up to go somewhere that's dangerous, whether that be a chemical leak hazard, a gas hazard, even places that are really hot, really cold, or we've had some fun ones lately where there's like an arc flash hazard. There's just a lot of dangerous stuff in the world that we expect people to do that robots could be doing. There's a couple of key things about the product. One of them is, we sell the product in a few different configurations. So one of them is, as a dev kit, and a thing that other companies can build their applications on. We ship a lot of robots as basic walking robots that come with a really highly polished Python API that you can implement production quality software on top of. But we also produce and sell a lot of end user interfaces for specific complete applications. So like if you want to take this robot and you have a facility that's full of vacuum pumps, say you're a semiconductor manufacturer and you want to walk around and take thermal images of your 3,000 vacuum pumps in your basement, we've got a tablet app that lets you do exactly that with no robotics experience. Why make a weird quadrupedal walking robot to do this stuff? It kind of breaks down in a few different ways. I think one of the most surprising things that customers have taught us that I think should have been obvious in retrospect is that infrastructure in customer facilities is really expensive and it's really hard to change. And customers want a way to introduce machines into their facilities that don't require them to change anything about their facility and let them kind of smoothly introduce more automation in their facility. They really like the idea of, I can just buy a robot, it comes on a pallet, and I can put another robot in my facility, and I can do that again and again without going through like a major integration exercise. These environments are surprisingly challenging. You might walk into an industrial facility and say like, oh, this is a structured human environment. I can get around here, no problem. One of my product managers formerly ran a wheelchair company. And I think that was like a very illuminating experience of his, where, think about yourself in a wheelchair, which is how a lot of robots get around. Unfortunately, in the modern world, you will have a lot of problems getting around. Things like cables strewn across floors, curbs, short gaps between concrete pads. If you look around with an eye for it, they're just everywhere. And so we make a robot that just kind of eats all that stuff up without a second thought. And you have a really strong abstraction barrier for what you're running on top of that. You tell that robot to go 100 meters forward and it'll get there. Then the last thing is, I think it makes a lot of sense to make a robot that is highly capable in a lot of different applications, because it lets us build critical mass behind supporting and fielding a single product. It's really hard to field a product, especially one that you kind of release into the world. That was another thing I really appreciated, was like when you get from the mode of like deploying robot, there's a big difference between deploying robots with a field team where you take it to a customer site and test for a while versus like, I have put this robot into a cardboard box and I'm going to tape it up and send them all over the world. And there's like orders of magnitude difference in terms of effort and robustness there. And you really end up needing a large team in order to do that work well. So you really want to make one thing if at all possible. Now, yeah, my pitch for Boston Dynamics, I love working at Boston Dynamics. I think it's awesome how short our pipeline is from research to product. So for example, this is an update to our mapping SLAM system that we shipped, last year or so. I think that went from people doing research in academic literature to literally shipping that product in about 6 months. And we're mapping buildings, we're doing bundle adjustment. They produce beautiful point clouds. I think we know how to nurture and how to ship things. It's not just like, okay, make your feature and get it out immediately. We know how to work on something for a long time. We're in some unique positions in terms of having a long-term vision and backing, but still being really serious about shipping product that customers are willing to pay for. Here's this is on YouTube, so it's not new to anyone. But yeah, like we're building and shipping stuff that folks in academia are submitting papers to ICRA today, saying, "Look at this great result," and like we're actually selling it to customers right now, which is I think kind of super cool. Okay, so bring impact to industry. So yeah, like I was saying, my personal view is that in academia, you don't need to do product style work yourself in order to make a really big difference in industry. I think from the position of someone in a PhD program or in a professorship, is probably thinking about like success for me is getting my techniques adopted, getting my ideas adopted, having strong relationships with industry, so that what I'm thinking about gets received and I have strong communication back to me about what's important to work on. Getting that direction feedback. Nobody likes to feel like they're working on something that isn't appreciated, and getting your contributions recognized. So like if you make something and then everyone adopts it, but nobody knows you made it, that's probably not a super great position to be in as a professor. So you want to get that too. And so I have at least a few opinions on how to do that kind of stuff well. First one is, there's a serious art and like there's serious work to be done to get your work out there in the real world. I pasted up some examples on the right, one shamelessly my own. But like I'm sure a lot of you are like familiar with three blue, one brown on YouTube if you're math nerds. Or the fact that like Gilbert Strang taught so many people linear algebra, or like the latest craze around images from Dali. Like these are examples of millions of people in the real world appreciating it's essentially kind of academic research, and none of this was without effort. Like this took like serious planning. All of these take serious planning in terms of thinking about your message, what you want people to take away from what you're seeing, thinking about how normal people interpret what you're showing them, and making sure that you show people things that will resonate with them without kind of the context of the rest of robotics industry knowledge around them. So yeah, you also really shouldn't be afraid of speaking directly to the public. So like going around conferences. So if you just present your work at a conference, your peers will see it and that's cool. But if you figure out how to package your work up in a way that you can get on YouTube, get views, if you can get a press release in the news, like you should be thinking about those angles and just how to make something that resonates with millions of people instead of thousands of people. Results that speak for themselves obviously matter. I think one of the hallmarks of our Boston Dynamics videos is that, at least for the robotics results videos, there's never a voiceover. There's never, music to distract you. We're just laying out the thing that happened at the lab. And I think if you can come up with something that, doesn't need someone explaining why you should be super impressed by it, then you really hit it. And yeah, all this stuff is like a lot of work. It's like, it doesn't just come. Second thing, I think, if I was going to say one thing to academics, it would be that, students and teaching are like so super important and critical. All the names are cut off here, but like, this is an example of a bunch of, somewhat recent graduates from PhD and master's degree programs at Boston Dynamics. It's a big company at this point, but like, the fresh blood from academia is really kind of the current of new ideas into an organization. And like, we do a lot of reading of literature, but like the really transformative stuff really requires someone who's like kind of been indoctrinated into, that new method of doing something. So like, when I started the company coming from Russ's lab, I was like super into trajectory optimization and like formal proofs of control over trajectories and like, and someone gets in the company and they just start pushing it that way. Like that's by far the best thing a professor can do to have an impact in industry, because like no one else in the world is going to be a stronger advocate for your techniques. So yeah, train lots of students, train your graduate students, and then just send them into the world and they'll go and implement all the things you've made. There's two other huge things that at least I see as really important from inside industry. First is like, you don't realize until you leave academia how much of a mess journal subscriptions are. And like, if, we really do go and read the literature and like, hey, we need a new feature detector. Like, what's the new hotness from academia? Let's go read archive. Like we read papers, but if your paper isn't available because it's, in a journal, it's going to be really hard to get seen. Good writing, like the same good writing rules for academia, totally apply for industry. This is like super basic stuff, but like, say why your result matters, explain what parts of what you did were the things that made the good result. Like a lot of times, the specific improvement to the technique is like hard to discern from the rest of the implementation in the thing. And if you can be ultra specific, like, oh, this magic term that I introduced into the heuristic is what makes it like find its way through the space so much better. Like that's gold. And then the last thing is example code that produces the actual result from the paper. Like if you're publishing something and you're like, hey, look at this cool Acrobat robot that swings up. Here's my pseudocode. It's really, really hard to take that and do stuff with it. Oftentimes because there's a lot of magic in the implementation. So like if you're able to, you really should just package up that whole thing and put it on the internet and let people mess around with the thing and replicate your result and play around with it and understand how to use it. Thing on the right, again, this is kind of simple stuff, but it's really true. Open source software. If you can produce code in the right kind of size and shape, what I'm calling working Lego bricks here, stuff that can actually be taken and implement it in a system that you probably haven't thought about, that's in a different framework than you work in. That's really important because, like, not everyone runs ROS. A lot of people run on embedded systems. So, like, if you're part of a big framework that requires you to like attach lots of stuff to it, it's really hard to use your work. And then having a permissive license, like a BSD license, that makes it super easy for people in industry to pick stuff up and work with it. There's tons of impact to be had there. I'm going to call out, one like obvious example of this is April tags. So I haven't seen Edelson since my time at MIT. But like, April tags are like super, super successful, and in my opinion, for exactly the reasons that I mentioned. And you see them like everywhere in our products. So like, we put them everywhere. Every time we have like a robot, like we just want to give it ground truth to something, we want it to find something, throw an April tag on it. We've even done like crazy stuff, like print like 15-foot wide April tags to do localization in a football field. And this stuff is like really successful because it's got a really good license on it. It's like in a small package that's easy to integrate into your system. It doesn't make a lot of, it's not super opinionated about what you plug it into. It does something super useful. And it does it to production quality, which like for something that does a pretty simple job, if you can keep it to a small amount of code, it's actually not too hard to get it to production quality, or not too hard to like test and debug it there. And so, that's like one super good example. Areas for collaboration with academia. So what are some things that I personally feel like we're not so good at in industry? And I guess this shouldn't be taken like absolutely. There's gradients to all this stuff. But in industry, even folks who do research in industry are focused on stuff that's like 3 to 5 years away. And the stuff that's like 5+ years out there, it's hard to work on. But it's super important for building the future. Analytical frameworks around things. So like, I think it's really, really easy to underestimate how critical the work, like, think of control systems, like your Laplace transform, and like the fact that someone figured out the analytical routes to how to plug all this stuff together and think about it. That is a super valuable thing that it's really hard to get folks in industry to do. In industry, you're always searching for results, and you're often not thinking about like, oh, well, here's a structure for how to think about this problem, and here's a cool math trick, and wow, that opened up this whole other thing. And then step changes in approach. And I think in most cases, we'll take the path of least resistance towards success. And just working on something a different way for the sake of doing it differently is a really cool thing that folks in academia often have the opportunity to do. So like I've got some pet problems here that I think are examples of this. This is like super myopic to the specific end of robotics that I play in. But I'd love academics to not step up, but just keep working on this stuff, because a lot of the excitement is coming from academia here. Dimensionally problematic planning problems. Like I'm seeing the this isn't academic, but the results from like AlphaGo are just like truly stunning to me as someone who has tried planning problems myself, and like seeing machines executing like long-term strategies for how to seemingly accomplish complex things, just like super amazing. And the world's the world of robotics is definitely going to change as we start seeing those results filter in. Machine learning and functional safety contexts. So functional safety is a super huge deal to folks who work with robots that can hurt people. So like the autonomous vehicle, people all know about functional safety. We work with functional safety because we work with robots that, can at least bruise you if they hit you. And there's a big gulf between techniques that are being super successful in machine learning for things like person detection and being able to like build a system that must function to not hurt a person. And huge opportunities there. And then analytical treatment for the design of learning systems. Like when I'm sure you're all going through the literature nowadays and like looking at these awesome results in reinforcement learning and supervised learning, and then seeing that like those crazy block diagrams of stuff plugged in this stuff that are like kind of intuitively made by folks. And we're kind of clearly in the pre-Laplace transform, pre-control systems thinking version of the world there. And we really need some analytical grounding, like folks to do some symbolic math and figure out how to make sense of all this stuff. So that's my kind of my request. How am I doing for time? Where did we end up?
You started a little late. We can go a little over it. You've got, I don't know, 5-10 more minutes of that.
Yeah, okay. I'll speed right through this stuff. There's a couple interesting things I think that can help you build product-ready robotic systems. The biggest of which is being super specific about what you're trying to build and like doing upfront design of your systems. I remember back to when I was being taught mechanical engineering, professors leaning into all of us about functional requirements, and you need to write this stuff down, and like, what's your full state diagram? And like, once you start building something the size of a robotics problem, you finally learn that like, oh, wow, that was actually super insightful. That's like the only way to control systems of this complexity. And even when you do that well, the stuff we work on is like just so big and complex and hairy once you introduce the real world that you still have to test it to death to get somewhere. But you really should do yourself a favor and do like really principled upfront design whenever you can. Design the complexity out up front. Do less things. Try to figure out what the real crux of the problem is, and then test it. Like, I think we've all talked about how important testing is. That's the foundation of making robots work well in the real world. And kind of the foundation of testing is figuring out what your customers are doing and testing the things that actually matter. This is one of my weird things that I've been working on, which is representation of a robotics company as a dynamic system. And this kind of explains what I'm saying about testing with customers. You've got a design team that designs robots. Your robot integrates up those design changes, and you run your robot, and it's really easy to measure what your robot does in your lab. Like, you can do a lot of that. It's really cheap for you. You can get thousands of hours a week. That's awesome. And then you've got this customer thing over here. And once you go through that, things get complicated because it's super expensive to test with your customers. But this is the state that actually matters. It's like, what is your customer happiness as they interpret the stuff that your robot does? So we spend a lot of effort thinking about this customer observer and trying to make all of our testing internally represent as closely what our customers are doing as possible. And that means like going out scouting local industrial facilities that we can do field trips to, building test labs internal to our building that represent customer facilities, thinking up or implementing super antagonistic lighting cases, like all that stuff. Like, that's a lot of the magic stuff, because it's really easy to test a lot, and it's really easy to test the wrong thing if you aren't paying a ton of attention to what your customers are doing. You sum all that stuff up, and the error signal gets back to your design team, and your software engineers crank away on bugs, your hardware teams crank away on ECOs, and you integrate that up in the product and you keep running that. And then there's this other cool thing over here, which is the organization itself learning. You look at the stuff you're doing wrong, and you put together engineering guidebooks and processes. And that's really where a lot of this process stuff that you see engineering companies doing comes from, is the kind of accumulated learnings of all the bad stuff that's happened with customers. And you turn that into engineering gates, design guides, checklists, and those are all your design feed forwards. So yeah, that's kind of how I think of the product robotics company. I think that's all. Yeah, it's a couple other academic focus things. Stay in touch with your students. That's like a super important relationship. Students should stay in touch with their profs. Stuff that's only like 30% better. It's like, industry is really good at working on that kind of stuff. Keep your like stuff small and digestible and easy to integrate. So, that's all. Any questions? That stuff?